everyone. So this is a video lecture for chapter 3, which is sampling distribution. Okay, so previously in chapter 2, we have learned about different probability distribution, like a discrete and continuous distribution, like a Poisson, and also the binomial distribution. And then we learn about the continuous distribution, which is a normal distribution. Okay, so this is sampling distribution, which is related to statistic. Okay, if for sampling distribution, which is you have a big population, and then you have some interest out of this population that you want to predict or you want to analyze. Okay, so it is impossible if you want to get all the data out of this population, of the whole population. So what we did is we took some sample of this whole population, and we can do some prediction or we can do some analyze data. Alright, so that is about sampling distribution. So before we go further, I will explain about the important parameter that we normally use in this chapter. Okay, so this is the population. Normally we denote this population as capital N, and then this is our sample size. We denote this as a small n. Okay, and then out of this population, we can also find the mean and also the variance of this population. Normally we denote this as the mean as a nu and the variance as a sigma. Okay, for sample size, we can also find the mean and the and the variance for this sample. Normally we denote the mean of the sample as the x bar and also the variance as a sigma. Sigma squared, and then this is variance of the population. We denote this as a sigma x bar. Okay, so when we took a sample, we can get the mean and also the variance of the sample, and then we can compare or we can find the sampling error of the mean. Okay, by doing the subtraction of sample mean minus population mean, and then we can get the error between the mean of the sample and the mean of the population. All right, so this is what we call as a sampling error, which is depends on the sample that we took. Okay, it may be a positive or negative value. That's why we have some modulus here. All right, that is sampling error, which is the difference between the value we get from the sample mean with the corresponding value of the average of the population. All right, and then from this population we can find the mean. Okay, we can find the mean, like I mentioned just now. The mean of the population is nu, and the mean of the sample is x bar. Okay, this is normally what we did when you want to find the average of the whole population or the average, the mean of the sample. Alright. Okay, so definitely if you want to find the sample mean, if we denote this as x bar, and then this is the nu, definitely the nu is not equal with the sample mean. Alright, that's why you can find the sampling error just now. Okay, if we took another sample here, we name it as a x bar 2, and the previous one is x bar 1, and of course the sample mean of this sample 1 with the corresponding sample x2 is not equal. Right? Sample mean 1 does not equal with the sample mean 2. Right? That is definitely obvious. Okay? But in some cases, or not in some, but in some theorem, what we call as a central limit theorem, we can assume that the sampling, the mean of the sample is equivalent with the mean of the population. Okay, that what we call as a central limit theorem. In the case of when the sample size is very, very large. Okay, we can look at this after this. All right. So before we go further, uh, let's prove, or let's find on how we can determine the mean and the variance of a sampling distribution. Okay, against the mean and the variance of the population. All right. So if let's say this is your probability distribution of X, we have learned this in chapter 1. Okay, this is the PDF distribution of the random sample of X. If let's say you have three numbers, 1, 2, and 3. Okay, this is the population. You have 1, 2, and 3 in the box. Okay, once you pick in the box, you can have some possibility, which is either you can pick 1, or you can have 2, or you can have 3. So all these are random sample of X. Okay, in order for you to get possible to pick 1 is 1 over 3. In order for you to your possibility to get number 2 is also 1 over 3. And also if in order for you to get number 3 is 1 over 3. That is the possibility. Alright. So this is the probability distribution of a random sample of X. And then from here you can find the population mean and the population variance. Okay. This is according to our previous formula, which is you can find the expected mean and also the variance using this formula. Then we can substitute this 1 times 1 over 3 plus 2 plus 1 over 3 plus 3 1 over 3, which is equivalent to 2. So that is population mean. We denote this as a nu. Okay. Another one is the population variance. Okay, population variance you can calculate by variance X is expected of X squared minus the mean squared. Alright, and then we substitute the value and then we get 2 over 3. Okay, so this is sampling distribution. Okay, sampling distribution means out of this population we draw at least 2 times. Okay, sample size of 2 is draw. You draw 2 times, like you are tossing a dice, for example. Then once you draw 2 times, you can have this kind of possibility: 1 to 1, 1 to 2, 1 to 3, up to 6 to 6 when you draw a dice. Okay, but this one is a sample size you draw 2 times. Okay, so you draw 2 times and then you can have this possibility to get the value out of this population. Okay, so you can have the combination of 1 1 1 2 1 3 until 3 3. Okay, so you can find the mean of this sample that you drawn just now. Okay, then you can get the mean is 1 plus 1 divided by 2 is 1, 1 plus 2 divided by 2 is 1.5, and so on. So from here you can have the sampling distribution, which is this is a random sample of X, and then the possibility of you can get this value is tabulated like this. Okay, so again from here you can find the mean and the variance. So this time we call as a mean and variance of a sampling distribution, because this is the sample that you took out of this whole population. Okay, and then we can find the mean and variance similarly like a previous example, like in previous formula. Okay, you can substitute all these values inside this formula, and then you get the mean of the sampling distribution is equivalent to 2, while the variance of the sampling distribution is equivalent to 1 over 3. So here you can prove that the mean of the population which is new, is equivalent with the mean of the sampling distribution. New x bar. Alright, well, for the variance of the population is equivalent to variance divided by the size of a sample, okay, which is 2 over 3 divided by square root of 2. Okay, so here we got 1 over 3. Okay, so that is we can prove that this variance, right? Okay, this variance of the population is equivalent to variance divided by square root of 2. Okay, this is the variance of the population, right? Variance of the population is equivalent with the variance of the population. Variance of the sampling distribution is equivalent with the variance of the population divided by square root of the sample size. Okay, so variance of the sampling distribution, we got 1 over 3. So it's proven based on the previous calculation, we got 1 over 3. So this is the formula. Alright, the mean of the population is equivalent with the mean of the variance, a mean of the sampling distribution, and then the variance of the sampling distribution is equivalent with the variance of the population divided by the square root of the sample size, which is n. Alright, so from here we can find the probability of the sampling distribution. Okay, so before that, like I mentioned just now, we have some theorem what we call as a central limit theorem. This is a sampling distribution of the when the sample distribution of the mean or random sample drawn from any population, we can assume that it is normally distributed. We can assume that it's normally distributed just in case if the sample size is totally large. Okay, we consider large here in case if n is more than 30. Alright, you can look at your slide that when your n is less than 30, your curve is slightly like this. When your n is somewhere less than 30, like a 20 or n equivalent to 10. Okay, once you increase the number of sample size n, and then your curve will be slightly to normally distributed. Okay, this is when your n is maybe around 30. Okay, and if you increase your n, maybe up to 100. Okay, so this is when your n is equivalent to 100, and then you can see that your probability distribution is normally distributed. Okay, is totally normally distributed when you can have it is the mean sample is very small, and the variance also will be decreased. Okay, how you can find the variance? You can see that under the curve is when it's large, it is the spreadness, what we call is the spreadness of the variance. Okay, you can see from the curve. Okay, when it is not at the peak point, you can see that the variance is spread largely. Okay, when you increase the number of n, you can see that the variance will be decreased. Okay, the spreadness of the variance will be decreased when you increase the number of size n. Alright, so once you increase the number of the number of sample size n, and then you can have the curve is totally normally distributed. Okay, so that is according to central limit theorem. When you have the large number of sample size, then we can assume that the mean of the population is equivalent with the mean of the sample. Alright, and we can assume that it is normally distributed. Okay, so now let's look at on how you can find the probability of sampling distribution for a single mean. Okay, so you using this to find the probability of the sampling distribution for single mean, we can use a normal distribution, and then normal distribution is normally the notation is like this: n, capital N, and this is the mean, and this is the variance. Okay, and then this is denoted as the sample. Okay, sample mean and the sample variance. Okay, and then this is from previous formula that we proved just now. The sample mean is equivalent with the population mean, and then this is the variance of the sample variance is equivalent with the variance divided by number of n. Okay, and then we can square root of this variance, and then we can get this is the formula for standard deviation. Alright, and then we can substitute using the normal exact standard formula. Okay, like previously we have learned this in chapter 2. Z is x minus nu divided by standard deviation, right? Okay, so we can substitute this. Nu is nu of the population, and standard deviation now is sigma divided by n. Alright, you can substitute this is the standard Z formula. You can substitute this for sampling distribution. Okay, so in order for you to find the sampling probability, so we can use this P of Z, and then you can find the Z value. We have some bracket here missing. Okay, let's look at this example. It's given that the population mean and the variance is 2.4 and 0.021 respectively. Okay, previously you have calculated this in the tutorial, I think. Okay, and then you get the mean is mean of the population, and then this is the variance you get from variance divided by number of n, square root of n. Okay, find the probability distribution that mean of sample distribution of x will be more than 2.8. Alright, so this is the mean of the population, this is the variance. Okay, so this is mu is 2.4, and then the variance is, which is sigma squared, is 0.021. Okay, and then find the probability for P of sampling distribution, which is x bar, will be more than 2.8. Okay, so we can just follow the notation. Okay, you can get this as a z, convert to z, and this is just similar to more than, and then 2.8 minus the new is 2.4, divide by, this is the variance. Okay, this is the variance. You can just, this is computed from sigma divided by n. All right, so you can just square root of this value. Okay, this is already calculated using sigma divided by square root of n previously. All right, so you can just square root of this, and then you get p of the z value is more than 2.7603. Okay, then you can use your formula using r. Okay, using r, you put in your calculator 2.7603. Okay, then you can get the answer is 0.00289. All right, so that is for single mean. Okay, let's look at another example. This is also single mean, where the average life of a machine is 7 years, is standard deviation of 1 year. Okay, so here we get the mean of the population, which is new is 7. Standard deviation of 1 year is the sigma of the population. Okay, is 1. Assume that the life of machine is normally distributed. Find the probability that the mean life of sampling distribution of 9 machines falls between 6.4 and 7.2. Alright, you have the 9 machine, this is n, sample size n, and then you want to find the probability between 6.4 and 7.2. Okay, so you can just substitute using the formula z value just now. This is p 6.4, okay, minus the mean is 7 divided by standard deviation of the population, okay, divided by square root of 9, and then this is, just follow this notation, zigzag. This is 7.2 minus 7 divided by, this is standard deviation, right? So this is 1 divided by square root of 9. Okay, standard deviation divided by n, so this is 1. Okay, so from here we can have p is equivalent to 6.4 minus 7 divided by 1 over 9, square root of 9 is minus 1.8. Okay, and then just follow the notation previously. This is zag, this is 7.2 minus 7 divided by 1 over square root of 9. Okay, this is 0.6. Alright, so if you plot the area, this is somewhere in the middle, like this. So you can use your calculator. So you can use either P, Q, or R. So the best way and the simplest one is use Q, alright? Because it is at the center point. Here is the 0, okay? So you can use Q 1.8, Q 1.8 plus Q 0.6. Okay, no need to put the minus sign. We assume this is mirror, so all are positive. Okay, so use Q, you get 1.8 plus Q 0.6. Okay, and then you get the answer is 0.6898. Okay, so that is the probability of having the life is between 6.4 and 7.2 years. Okay, so that is for single mean. Alright, single means meaning you have one population and then you get extract one sample out of the population. Okay, next is sampling distribution of difference between two means. Okay, so at this point you have two population here. Maybe you want to compare between region 1, region A, and then region B, and then you can get the difference, for example. Okay, you have these two population. Okay, maybe you want to get the uh, population in Selangor compared to the population in Sabah, for example. Okay, so you cannot get the whole population. You cannot extract the information from the whole population in these two regions. What you can do is you can just get some sample of this population. Okay, from this population, from region A and region B, and then you can get the difference between these two populations. Okay, what you can do is you can find the sample mean. This is the sample mean A, and then this is the sample mean B. Okay, and then we can have some difference. Okay, you can get the difference between two means. Okay, and then you can also find the standard deviation of the variance of these two means. Okay, so this standard deviation formula, which is the variance between these two means, also we can call this as a standard error of the difference between two means. Alright, same like previously, we know the sampling error of the single mean, which is the difference between the sample mean and also the population means. Okay, here is you can compute the standard error, which is the difference between the two means. Okay, and again, according to central limit theorem, like previously, remember when your sample size is totally very large, it is sufficient, more than 30, we consider is larger. Okay, consider is large, and then we can assume that the sample mean for region A and the sample means of region B is normally distributed. Okay, the difference is normally distributed. You can assume that it is normal distribution. Okay, so like a previous single mean, we can also find the difference between two means, find the probability difference for two means. Okay, using the like a previous step just now, you can find the mean first, the difference between two means, and then you get the standard deviation of two means, and then you compute the z value. Okay, like previous example. Okay, let's look at this example. This is difference between two means. The length of computed dust is approximately normally distributed. Okay, there are two factories which produce that kind of dust. Alright, which is factory A and factory B. So this is population A, and then this is population B. Okay, we get some sample out of these two population, and then we compute the sample mean, which is 0.60.5 for factory A, 58.3 for factory B. And then we can compute the standard deviation for both sample size. We get 3 for factory A, and factory B we get 4. Alright, and this is a sample size that we took from factory A, 35, and this is sample size that we took from factory B, which is 40. Okay, so back to the questions. Find the probability that the mean sample for the length of computed dust produced by factory B is greater than the mean sample of the length of computed dust produced by factory A. That you want to find the probability that the mean sample for B is greater than the mean sample at factory A. Okay, this is new, yeah, mean. This is new. Okay, so first we compute the difference between two means. Difference between two means is mean B minus mean new A. Okay, so we get the 60.5 minus sorry, not enough space. Factory B, new B minus new A, which is 58.3 minus 60.5. Okay, and then you get this as minus 2.2. Alright, and then we compute the difference of two means. Compute the standard deviation. Okay, compute the standard deviation of two means. So this is the formula for difference between two means. Variance of the population 1 over n plus variance of population 2 over n. Okay, so according to that formula, we compute the difference or the variance between factory A, B minus A is equivalent to 3 variance for the population, right? 3 power of 2 divided by 35, and then plus 4 power of 2 divided by 40. Okay, so you calculate this, you get 0.65657. Okay, alright, and then you can get the probability between difference of factory P minus A just now. We want to find the probability that B is greater than A. So XB is more than A. Okay, xb is more than xa. Okay, it's equivalent to 0. All right. So this is just mathematics. You pass this, go to the left side, and then this is more than 0. Okay. So nu b minus nu a is more than 0. Okay. It's just like a mathematic, right? Once you cross to another side, so this one become minus nu b minus nu a, and then this one become more than 0. Alright. So we compute the z value here, minus the mean. So now 0 minus 2.2 minus 2.2. Okay. Divide by the variance just now. So square root of the variance is 0.6571. Okay. And then we get this as a p-value. The p-value is z more than 2.71. 2.714. Okay, so you can find from your calculator, pz more than 2.714 is equivalent to 0.0034. Alright, so this is the probability that factory B produce a greater dash compared to factory A. So this is the probability that factory B produce greater computer dash compared to factory A. Alright, so that is how we can find the probability between two populations. Okay, we compute the sample mean, and then you find the difference. You compute this variance and variance of the two means, and then you can for difference from two means, and then you substitute it into the z value, and then you can get the probability. This is the probability distribution between two sample mean. Okay. So we have covered the sampling distribution for single mean, and this one is sampling distribution for difference of two means. Okay, so that's all for chapter 3, which is a sampling distribution. Alright, you can carry on with your tutorial. Okay, thank you.